Okay, good afternoon, everyone. So I'm Dr. Mattia Negrello. I'm an astrophysicist, and I'm also a senior lecturer here at the Cardiff School of Physics and Astronomy. And I teach a third-year module on cosmology, so about the study of the universe. And I'm going to give you a 10-12 minutes mini lecture inspired by my cosmology module, essentially to give you an idea of how I deliver my lecture. And I normally use two instruments to deliver the lectures, which are PowerPoint slides and handwritten derivation done with the iPad, which is exactly what I'm going to do in this mini lecture. And because this mini lecture is inspired by my cosmology module, it is about a cosmology topic, which is the expansion of the universe and the significance of the Hubble's law. So the Hubble's law, it's a relation that was published in 1929 by Edwin Hubble. You have probably heard the name of Edwin Hubble. Usually Edwin Hubble is associated with the discovery of the expansion of the universe, but that is not correct in the sense that Hubble did not discover the expansion of the universe. People already knew before 1929 that the universe was in a dynamical state, it was expanding. And so what I'm going to explain in this mini lecture is the significance of the discovery of Edwin Hubble in relation to the expansion of the universe, okay? So first of all, let me tell you that the universe is made up by many different things, but in particular, the visible building blocks of the universe are this beautiful system. You can see a gallery of them in here, which we refer to as galaxies. These are systems made up of hundreds of billions of stars. They come in different shapes and forms, as you can see in this beautiful image from the Hubble Space Telescope. And it is estimated that in the observable universe, there are more than 1,000 billions of this system. And we happen to live in one of these systems that we refer to as the Milky Way. Okay, so we use this system essentially to trace the dynamical state of the universe. And as I already anticipated, the people already knew before 1929, before Hubble published this relation, that these galaxies were moving, and in particular, they are moving away from us. Okay, no matter the direction in which you look from our position in the universe, we see that galaxies are moving away from us. And that clearly indicates that the universe is in a dynamical state, and in particular that the universe is a sort of expanding. And so the question is, how can we model this expansion? Well, the simplest model of an expansion we can think of is an explosion. If you have an explosion, you have debris moving away from the center of explosion, okay? And this is exactly what galaxies are doing. They are moving away from a point. And this kind of model raises some issues because if we use this kind of model to interpret the expansion of the universe, we have to conclude that we are located at the center of the expansion. And this is a problem because it implies that we are in that special position in the universe, unique position where the universe is basically at rest. There is nothing happening. And you might think, okay, what's the problem? It's just by chance that we happen to be there. Okay, it's a coincidence. But let me tell you that scientists, they do not believe in coincidences. We always need to come up with an explanation for everything. Besides, history teaches us that every time we thought we were at the center of something, we were wrong. In the Middle Ages, we thought we were at the center of the solar system. We proved wrong. Then at some point in the 18th century, we thought we were at the center of the Milky Way. We were wrong. We are not at the center of the Milky Way. And then up to the early 20th century, we thought we were at the center of the universe, while instead we know now that the Milky Way is just one of the thousands of billions of galaxies out there, and we are not at the center of anything. Okay, and this idea that we do not occupy a special position in the universe is what we refer to as the Copernicum Principle. Okay, so there is nothing special about the position we occupy in the universe, and that means that if we observe something about the properties of the universe from our position, we should be observing the same even if we were living in any other galaxy in the universe. In other words, if we see galaxy moving away in all directions from our position in the Milky Way, we should be observing exactly the same galaxy moving away from us, even if we were living in any other galaxy in the universe. And so at this point, okay, so all galaxies in the universe should be moving away basically one from the other. So at this point, the question is, how can we model can we think about an expansion where basically everything is moving away from everything else? Okay, in other words, an expansion with an infinite number of centers of expansion. And this is basically the point in which we need to abandon our standard common idea of space as something static, unchanging, and embrace this crazy idea brought forward by Albert Einstein with his theory of general relativity, according to which, sorry, let me rerun this, according to which space is not static and unchanging, but actually is more like an elastic fabric that can bend, can stretch, can change with time. And so we can use the model of an inflating balloon to describe the expansion of the universe, okay, as represented in this cartoon, in this animation. Essentially, imagine you have an elastic balloon that is being inflated, and that the surface of that balloon represents space. Of course, this is a two-dimensional representation of space. Oh, oops, sorry. This is a two-dimensional representation of space, okay? But this is the only way in which we can visualize this, and it delivers the idea. Okay, so you have a space that is being stretched, and galaxies live in this space. And so as you stretch space, these galaxies are dragged away one from the others. Okay, and so in this context of general relativity, the expansion of the universe is basically a consequence of the stretching of space itself. Okay. And this leads us essentially to this Hubble's law. Okay, so as I said, this is an observational relation that was published in 1929 by Hubble between the speed, the velocity, this one, at which galaxies are moving away from us, and the distance at which galaxies are. And the plot you can see in here is the original plot that was published in 1929 by Edwin Hubble. There is a lot of scattering in the point, but essentially they are clearly indicating that there is a relation of proportionality between the velocity and the distance, the constant of proportionality being the so famous Hubble constant. Now, this relation is extremely important in cosmology because essentially it is a demonstration, not that the universe is expanding, okay, but that the universe is expanding according to general relativity. So with this idea that space itself is stretching, by doing so is dragging away galaxies one from the other. In this sense, it's not correct to say that Hubble discovered the expansion of the universe. What Hubble did with this relation was to demonstrate that the universe, of course, is expanding, but it is expanding exactly in accordance to the theory of general relativity as a consequence of the stretching of space, okay? And I wanted to conclude this lecture by doing a very simple calculation using the iPad. So let me share my iPad, just to convince you about this. Okay, you should be able to see my iPad now. Okay, I want to do a very simple calculation to convince you that in a universe that is where space is stretching, you end up with a linear relation between the velocity and the distance of galaxies. Okay, now the nice thing of using the iPad is that I can draw perfect circles. Okay, and imagine that this is that inflating balloon that I was showing before. In this case, it's even simpler because we are considering a one-dimensional surface of a circle. So this is basically space, 1D space, okay? And let's consider, let me call first of all with the capital R, the radius of this space, okay? And let's consider two galaxies along this space. So this is my representation of two spiral galaxies, okay? And let me indicate their separation along space with the capital D, okay? And I want also to indicate the angle subtended by these two galaxies, which I call theta, okay? So this space is stretching, is expanding, okay? And I'm going to make an assumption. I'm going to make the assumption that it is expanding at the same rate everywhere. What is the implication of this? The implication of this is that this circle, while expanding, is not being deformed. It keeps its shape, okay? So if this is the circle after a certain amount of time, what happened is that, of course, galaxies have moved away one from the other. You can see that the distance here has increased, okay? But because of the hypothesis I've made, during this expansion, this angle has remained constant, does not change, okay? And so I can express, by the way, the distance as the product of the radius and the theta, if theta is expressed in radians, okay? So having set this up, now the question is, what is the velocity at which these galaxies are moving away one from the other? Now, the velocity, by definition, is the time derivative of the distance. I don't know if you have come across the concept of time derivative before. It's essentially how a function is changing with time, is a measure of that. But if you haven't, don't worry, it's something you will learn at least in the first year at university in the maths course, okay? And this, to make the notation lighter, very often the derivative is indicated with a dot on top of the function that you are deriving, okay? So if I use this relation, okay, I can write this as the derivative of capital R times theta. And now I can use the properties of the derivative, which tells me that if I'm taking the derivative of a function multiplied by a constant, I can just take the constant out of the derivative. Okay, and so I can rewrite this as theta times the derivative of capital R. Okay, and now I'm going to do a very simple trick. I'm going to multiply and divide this relation by capital R. Okay, why I'm doing that? Because theta times R, again, you can see from the relation above, is just the distance, okay? And so I end up with this relation, V, which is a function of time, is equal to the derivative of R divided by R, which are all a function of time, times the distance, which is also a function of time, okay? And so you can see in here that for any fixed moment in time, you have a linear relation between the velocity and the distance. And if I calculate this at the present time, which I normally indicate with T naught, okay, present time, what I get is V T naught equal to this function basically calculated at the time at T naught. So it becomes just a number, times the distance between the any two galaxies at that moment in time, the present time. And this, which is just a number, is actually the Hubble constant. So the Hubble constant is just the value at the present time of this more general function, which depends on the expansion rate of the universe that in cosmology we refer to as the Hubble parameter. So this simple calculation shows you that indeed, if the expansion of the universe is a consequence of the stretching of space, okay, you end up having a linear relation between the velocity at which galaxies are moving away and their distance, which is exactly what Hubble has found. So let me remind you, Hubble did not discover the expansion of the universe. Hubble proved that the universe is expanding according to the laws of general relativity, okay? So I hope this was clear, and if you have any questions, you are welcome to ask. And I think I can stop the sharing.
Thank you, Mattia. Yes, an excellent demonstration of simple maths showing, or relatively simple maths showing something quite profound when it comes to us. So thank you for that. If there are any questions in the chat, then please feel free to ask. Hopefully that gave you a flavor of the different types of teaching that can take place. So obviously we're restricted right now to doing stuff online, both not only for this session, but actually for this period, this semester at the moment, and this year rather. But even so, we can do a number of things. So you saw Mattia using his iPad, doing some maths, and put yourself in the shoes of a student who could sit there and copy down that maths if they wanted live, or our lectures are always recorded. So go back and rewatch that recording. If they lose track of it, to go back and say, I don't quite understand what that meant, then go back and watch the recording at a later stage as
and
well.
also, let me say, Chris, that all the iPad notes are made available to the students. So at the end of each lecture, I just upload straight in Learning Center, which is our platform for all the teaching material, both the videos of the lecture as well as the PDF generated from this. So this is made available. Okay, you can see. Okay, this one is immediately converted into a PDF and uploaded.
So we've got a question come in. Alex has asked, the symbol used in place of equals in V equals HD for Hubble's law, what does that mean for the law?
The symbol used in place of equal?
Was there did you do a proportional, or was it it was an equals, was it? Or
yeah, no, it was an equal.
Okay.
Yeah, there is a direct proportionality between the velocity and the distance.
Okay. So you can think of V as proportional to D, where H is that constant of proportionality, if you're thinking back to proportionality. Excellent. Okay. If you have any more questions, then I think Mattia is happy to stick around while Phil gives his lecture, and there'll be time to answer questions at the end as well. So feel free to type in the chat as we go, and we can always come back to them after Phil's talk if that's good. Or stick your hand up if you want to ask a question as well.